Hello, everybody, and thanks for coming today to this open hour. This session is going to be on thermal imagery and the tools that we use for it and the different ways that this data is helpful. So we have a number of speakers today, and I'm actually going to pass it over to Liz Berry in New York to introduce some people who are with her and talk a little bit about some of the things that speakers we should be hearing from today. And if anybody is just watching this, and I'm going to annoy several people who are already on because I'll say this a couple times, but if we have viewers who aren't live and are interested in getting on the live call, you can hit the Join the Call Live button on the OpenHour page and join us right in here in this call. Otherwise, you're welcome to join us in the chat room, which is also on the OpenHour page. And we can field questions, comments, and everything right into the live call from there. So thanks a lot, and I'm really looking forward to it, and I'll pass it over to Liz.
Okay, great. Let's see. So the three presenters we have here tonight all do really wildly different things with thermal imaging. We're going to hear from Ned Horning, who is an expert in Landsat at the American Museum of Natural History, and he's excited to get lots of question and answer. Leela Prashad is many things, including on the ASTER research group, and ASTER is an instrument that's really good at getting thermal data, and she's going to present a bit about her work. And then Zenon Tekzarny has made a really great visualization out of some thermal imagery related to pursuing better regulation against a nuclear power plant in Massachusetts. So I'm excited to hear about in New Jersey?
Yes.
Oh,
Oyster Creek.
It was Pilgrim. No?
No, Oyster Creek.
Oh.
Yeah.
So we have even more things to learn about today. That's who we're going to hear from, but I have a lot of people with me in New York, so I'm just going to kind of let people go around the room, starting with you.
Hi, Steven. I am Jay Holmes from Museum Network. I am Jeremy.
Sweet. Great, that's us here.
Cool. So who's interested in going first? Do I have any takers? Can I pick on one of you?
Pick
All right, Zenon, you're right next to my name here. Do you want to go first?
Well, I can go first, although I feel like I might not be the best to go first, just because I probably know the least about thermal imagery than everybody else. But you know, if nobody else wants to go, I'd be glad to go.
Do I have another taker to take the heat off, Zenon?
I can go first. That's fine. I don't know if it's too technical or not, but.
Oh no, it sounds great. And we have, I'm just monitoring the viewers here, so we've had a few more join on, so let me just do my little spiel for a second again, maybe while you get ready. Do you know how to screen share if you need to?
Yeah, I do.
Okay. So just for anybody who's watching, you are also welcome to join us in the live call. We have several spots available, and you can get there from the Join the Live Call button on the OpenHour page. And you can also join in on the chat room if you'd rather just watch, and we can field comments and questions right there from the chat room page. So I'm going to post the link again on the chat room page to the Join Now button, and feel free to meet us in here. Otherwise, sit back, relax, and let's learn a little bit about thermal imagery. All right, Leela, thank you.
Okay, thanks. This is Leela Prashad. I'm going to talk a little about my research with thermal infrared remote sensing. I'm going to keep it very short, so please ask lots of questions. So I don't know how much experience people have with satellite imagery, but satellite imagery, particularly things like Landsat and ASTER and MODIS, are passive instruments. They are recording radiance and emission from the surface of the Earth, and those emissions, radiance, has to go through the atmosphere. So a lot of times you'll hear the thermal infrared talked about in micrometers, and the wavelength of that part of the thermal infrared. So oftentimes we're talking about the 5-micron range through about the 15-micron range. You'll notice here, yeah, you can see my mouse. So this squiggly graph, these troughs are the areas of the electromagnetic spectrum that can go through our Earth's atmosphere. So because we have, yeah.
For 2 seconds, we're not seeing your individual slides. If you want to click on the one slide to pull it up.
Can you see that?
That's better.
Okay. Sorry, it's
screen view, and we would see the same thing you're seeing. But that works fine.
Okay, cool. All right. So just that, like that, this part right here. So what you see with your eye happens to be what we call visible light, and plants are reflecting very strongly in the near infrared, which is just past the red, right about here. The thermal infrared is basically in this region, and there's this nice empty space here where our atmosphere allows transmission of these wavelengths, especially around 10 micrometers. So a lot of satellites take advantage of this, and they put their bands in the thermal infrared right around this area. So this is sort of an opposite graph. Here the pink is showing the amount of transmission through the atmosphere of thermal infrared wavelengths. And so, for example, Landsat, one of the older versions of Landsat, the Enhanced Thematic Mapper, has one band, one number in the thermal infrared. Aster has 5 bands. So that means that Aster has a better spectral resolution of the thermal infrared over the older Landsat. The newer Landsat has 2 bands in the thermal infrared, so 2 numbers. So some of the things you can do with the thermal infrared, let me zoom out a little bit here. So I think the thing to take away from this for you guys is that the thermal infrared is good for temperature, which you probably know. It's also good for composition, and that's because every material has its own emissivity. It emits thermal infrared wavelengths in its own way because of the chemical composition, the way that the atoms are vibrating within that type of material. So for every type of geologic material, every rock type, every urban material, a concrete and asphalt, a pavement, trees, everything is vibrating, and you can use spectroscopy, you can use thermal infrared information to map these. So here, you see some squiggly lines that kind of look like our atmospheric transmission. These are the individual emission spectra of different kinds of material. So quartz and feldspar, these are different rock types. Each of them has its own pattern. And so you can use the bands of a satellite. Say Aster has 5 data points, Landsat has a couple. Here in this case, we have this blue line, this green line, this red line. Those are taking 3 slices, 3 points on each of these spectra, and mapping them to visible red, green, and blue, coming up with this false color image. So red on this image is mapping to the amount of intensity at each of the points in these emissivity spectra. So you can develop, you've probably heard of false color images. These false color images actually talk about composition, and you can use them for cities too. It's really much better if you can get an airplane to fly a thermal infrared sensor. But here, you see these different colors of this. This is looking down onto a city environment. Maybe you're familiar with land use classification. This is a much better land use classification because every material has its own emissivity. You can map it very well. You can also, of course, use thermal infrared remote sensing for temperature. You've probably heard of the urban heat island effect. You can look at temperature patterns within a city. Streets are hotter, vegetation is cooler. And so that's the basic crux. You know, some of the things you might hear are radiance and emissivity and black body. You know, if you start to get into this, you can get into a lot of physics, but the main thing to remember is you can use the thermal infrared remote sensing imagery for both composition and temperature. So I wanted to keep it pretty short to, you know, just a few minutes. So that is what I have. And then, you know, I'll be happy to take questions later.
Great, thank you. Does anybody have any questions right now for Leela, or we can do these questions as well later if you think of them? And you can submit them in the chat, or if you're in the live call, go for it.
This is Liz, and well, I can't help but ask how this kind of hyperspectral imaging relates to the handheld spectrometers that are now very widely used in the public lab community. Could you make any comparison for us? Or maybe someone else on the call could just briefly discuss that to relate, you know, just to relate it to something we've actually picked up and used ourselves.
Yeah, I think someone else should talk about the instrumentation, because I'm not entirely sure what wavelengths you're looking at with that handheld.
I can take a shot at it. This is Ned. Can you hear me?
Yeah. Yes.
Okay. And somebody else can chip in if they can add something. But the handheld spectrometer that the PLOTS folks are using is more or less a relative instrument, so it's not really giving you actual units that you can compare. The data that you would get from a hyperspectral satellite sensor or airborne sensor or anything like that would give you a similar shaped curve, but it would actually have physical units that you could use to help identify features like Leela was just talking about. So the PLOTS instrument is more of a relative type instrument, whereas the satellite and airborne instruments are typically calibrated so you're measuring actual power units. You're measuring watts effectively.
Yeah.
That can be then converted to other stuff.
You're essentially using filters for your spectrometer.
They're using a diffraction gradient, diffraction grating, sorry, to basically split the wavelengths, and then they just take a picture of it.
Yeah, I think that's probably in terms of the technology, that's one of the major differences when you have Aster. So Aster is not hyperspectral. It's got 5 data points. You know, even Landsat, but you know, something that's hyperspectral, like that image of the city. I mean, all of that is digital. So they're not taking. It's not a photo necessarily. I guess there's all images. All photos are images, but not all images are photos. So thermal infrared imaging, the way I've just talked about with spectroscopy, it's, you know, it's measuring digitally the radiance at each of these wavelengths, or at a set of wavelengths that makes up a band. So you can certainly get, if you have a handheld spectrometer like that with the diffraction grating that's taking a photo of that, you can get an approximation, and you can get a temperature. It will be hard to do compositional analysis in the way that you could with a digital, a different kind of instrument. But you can get you can certainly get a good sense of what's going on, and you're on the ground. It's a higher spatial resolution measurement.
Great,
yeah,
thank you.
The PLOTS instrument also doesn't go into the thermal, so it's just into the near infrared. I forget how far out it goes. It might be 1.1 microns or something on that order.
Okay, well that's great. I mean, and say you only had a thermal infrared instrument like a FLIR, or well, the FLIR has others, but the near infrared is so important for the vegetation. The thermal infrared is not very useful for vegetation difference because it's all reflecting in the near infrared. It's not signatures of these different materials. It's more useful for things like built materials or geologic materials or soils.
Great, thank you. All right, Ned, did you want to go?
Yeah, actually, I think that might make sense. And thanks, Leela, for the good background, because I didn't prepare anything thing for that. So I think this will be kind of a next step. And I'm going to try to share my screen here. And I've been working a little bit with some folks that are working at the Pilgrim nuclear plant
Thank you.
off of Cape Cod. Can people see my screen, first of all, the screen sharing?
All right. Ned, did you want to go?
Yeah, can you hear me? I think that might make sense. And thanks, Leela, for the good background, because I didn't prepare anything for that. So I think this will be kind of a next step. And I'm going to try to share my screen here. I've been working a little bit with some folks that are working at the Pilgrim nuclear plant
Thank you.
off Cape Cod.
Can I just interrupt you for just a second and make sure that everybody has muted their microphone who's not speaking? I think maybe somebody has both the audio version and the live version going. Okay, sorry, Ned. Go ahead. Thank you.
Yeah, I'm not sure what happened there, but I just heard myself twice.
I did too.
Okay. So anyway, and I'll just go over some of the stuff that I went over with the folks working to study. They're studying the water coming out of the plant into the ocean. They want to study some of the plumes, and they're want to have fairly high resolution imagery, so they're using Landsat imagery. The Landsat satellites are the newest Landsat satellite is acquiring data every 16 days, and there's an older satellite that's also acquiring data every 16 days, and they're offset. So every 8 days or so, you can get an image pretty much anywhere in the world, really. And if you're interested in getting those images, you can get them from the USGS. They're all freely available. And this is the site that I have displayed here. It's called GLOVIS. This is just one of the sites where you can download images. And the URL is glovis.usgs.gov. And GLOVIS is just GLOVIS. And I think it's a fairly easy site to learn how to use. And there are some tutorials and guides and help and all that if you have some problems or questions on looking at those data. But the thermal data that are available on Landsat, the data are acquired at 100-meter resolution. They're actually, when you download the image, it appears like it's a 30-meter. It appears that the resolution is 30 meters, but it's just because it's subsampled. The instrument itself is acquiring the data at about 100 meters, just so you have an idea of how much detail you have. So every 100 meters on the ground has a temperature reading, and it's a square. And when you put all those squares together, you get an image, kind of like this one that's up there now. And the image, the latest, most recent Landsat data, like Leela was saying, it has two bands in the thermal, in the sensible heat kind of thermal, the kind of thermal we're interested in. And the reason they put two bands is so they can calculate temperature more accurately, surface temperature more accurately. Unfortunately, they're having problems with the calibration of one of the bands, band 11. So right now, we can't easily get calibrated surface temperature. What we can get, though, is what they call brightness temperature. And brightness temperature, the way I like to think of it is it's the temperature that the satellite can see. So the satellite doesn't really know that there's atmosphere between it and the Earth. So it's trying to measure the temperature, and it assumes that there is no atmosphere. And it calculates the reading in watts, and then we can convert those watts into what they call brightness temperature. And again, brightness temperature is just surface temperature that is not corrected for atmospheric effects. At least that's the simplest way to think of it. And for the folks at Pilgrim Nuclear Plant, that's not a huge issue because they're mostly interested in the relative temperature changes. So if they don't need to know exactly what the temperature was, at least this is my understanding, they're mostly interested to see the plumes. They want to see the differences in temperature across their study area. and with brightness temperature, we can get that. We can get very accurate measurements of the difference in temperature. It's just more difficult to get actual surface temperature, unless if you have some buoys out there measuring surface temperature, or you have some other surface temperature data, you could use that to calibrate it. But there's no way that I'm aware of, at least right now, to easily calculate surface temperature. And if you want to, when you download the image, it just basically has a bunch of numbers. It's just pixel values. And if you want to convert that to brightness temperature, you need to run it through some calculations. And if anybody is interested in doing this, you can just email me, or maybe we can figure out an easy way to distribute this. But today I put together a script. There's a software program called R that I think more and more people seem to be using, so that's why I did it in R. But it allows you, all you need to do is give it the path of the directory where your data are, and it'll read the metadata, it'll read everything it needs to read, and it'll create a brightness temperature image. And I can just show you what that looks like. So this is that area off Cape Cod. This little hook here is Cape Cod. And this is a brightness temperature image. And these dark areas, these dark spots, would be clouds, and they're dark because they have low temperature, because clouds are cold. These hot areas would be, this is a city, and you can see the ocean is a bit cooler, and you can see there's some clouds in the ocean, the little dark splotches. And I can just show you, I converted this to Fahrenheit just because I figured that's what most people are interested in, but the brightness temperature units are typically in Kelvin, but Kelvin's a little bit more difficult to understand because we're not used to it. But here, the brightness temperature for this part of the water is, in the mid-50s. Over this area, it's, high 80s, 90s, something like that. And that would be degrees Fahrenheit. And again, it's brightness temperature, which is close to surface temperature, but it's not actual surface temperature. If we knew some of the surface temperature readings here, so if I knew that there was a buoy here, and I knew that surface temperature reading from that buoy, and I had there were a few buoys, I'd be able to do a calibration to calibrate it to actual surface temperature. I think that's about it for now. But again, I'm happy to take questions if anybody has any questions.
Great. Does anybody have any questions for Ned right now? Or we will also have a discussion later.
Any questions here?
Yeah, just one question for Ned. If you had used any Aster surface kinetic temperature, the higher level product for the project.
I couldn't. You got garbled there for a minute. Sorry.
If you tried using any of the Aster surface kinetic temperature, they have a higher level product that's it's a temperature emissivity separation to create a surface temperature, a kinetic surface temperature. I was wondering if you had if you had looked to see if there was imagery available, or if you'd used any.
No, I didn't check, and I should have prefaced my little spiel by saying I don't actually do much thermal work. So I know enough to be dangerous, I guess. So I know. I mean, I have done some thermal work, but I rarely work with thermal data. So I haven't worked with Aster thermal data in probably 10 years.
Oh, okay. Well, it's Aster has its own problems because it's not always acquiring imagery, so you may not get exactly the day and time that you want. But it might be worthwhile to see if there's any available, and I'd be happy to. You have to pay, but I mean, any educational use is always free. You just have to put it in a little bit of a form. So if you're interested for this project, I'd be happy to get some. But yeah, I mean, it depends on if there's any available for the time you're looking.
Right. Okay, good, thanks.
Great. Xenon, do you want to go?
Oh, wait, hold on. We've got one more. Sorry.
Oh, you have one?
Yeah,
okay,
we have one.
No.
No,
we can't hear you. You'll have to come up.
Really little. It's her. Right there. Yeah, it's her.
Okay, so where I am?
There.
No,
you're there.
Oh, okay, that's nice. Well, now I'm huge. So I have a question actually regarding the calculation of the temperature from the Landsat. So I'm aware of the calibration issues, but I was wondering if you will totally discourage the use of band 10 as well to calculate the ground temperature, not the brightness.
The use of what? Can you say that one more time, just a little bit louder?
Oh, so there are problems, right, of calibration to calculate the temperature from Landsat. But there are two bands on the thermal from Landsat. And it's my understanding that actually it's the band 11 that is the most problematic. So I'm asking if band 10 is also out of the question in order to calculate the temperature. If it will be viable or not, will be. That's what I'm saying. Basically, will you trust it or not? Because I think some people are doing it, so that's what I'm wondering.
Yeah, I'm not the best person to ask, but my understanding is that NASA is still recommending the use of band 10 for doing the brightness temperature work. Eventually, people want to use there's a technique called the split window technique where you can use 10 and 11 to calculate surface temperature. But my understanding is that they're still having calibration issues with 11, band 11. I think it was the notice went out last fall sometime.
Right. So what I'm asking is, will you use band 10 only, even though you cannot do the split window algorithm, just some atmospheric correction?
Yeah. Well, for this work, I'm using band 10 just to go to brightness temperature, because these folks are mostly interested just in relative changes. So that the brightness temperature is fine for that. If they don't need to know the absolute temperature, and if they do need to know the absolute temperature, I mean, I've suggested we could look into using some other sea surface temperature data to calibrate it. There's some other things that we could play around with, but I think the main thing that they're interested in is just identifying the plume, the shape of the plume, the size of the plume, things like that. So for that, the brightness temperature should be fine.
Are you working on a particular project?
I've been working with some of my students on actually getting the temperature. So yeah, we can talk later about it. What happened with it. So that's why I was interested.
Oh, great. Okay, cool.
Great, thank you. Zenon, are you ready?
Yeah, for sure. So I don't know if I'm the last presenter, but I think that it was probably better that the order was a little bit different, because I think Alila did a great job at introducing the subject, and then kind of talked a little bit more about how it could be applied in terms of monitoring thermal plumes. And I have a project that I worked on almost 10 years ago now as a sophomore in college, so it's a little dated. And my familiarity with the subject matter is a little rusty, at least at this point. But maybe it will be a good introduction in terms of maybe how people can approach visualization of thermal pollution. So for those that have seen on the Public Lab blog, I posted this video that I did quite some time ago. And actually, let me set to screen share. This screen. Is this working? I don't know.
Yeah.
Okay, so let's see if the full screen works. I know that you guys are having some issues with presentations and whatnot. So this is the video. It's called A Year of Thermal Pollution, and it's kind of a collage almost of Landsat thermal infrared imagery, kind of modified to show the plume from Oyster Creek. And can you see my mouse?
Yes.
Okay. So Oyster Creek nuclear facility is right here. I chose really to simplify the image to really emphasize the size of the plume or the shape of the plume. And so why don't I play it, and I'll explain a little bit how I made this. There are some sophisticated approaches or things about it, and then not so sophisticated things about it as well. So let's see. Oops, it's already. Let me refresh it. Okay. Oops. So yeah, it's a year of thermal pollution following its animation. You can read it. And so it's more artistic maybe than scientific, one could say. But this is so yeah. What you can see here is that it goes throughout the year. You can see the image that is taken from Landsat 5, Landsat 7, thermal imagery, the band, and the date. And so what my goal here was to take various snapshots of the plume throughout the year and morph them together to kind of paint a picture of the spread, the scale of the plume and how it affects the bay and the estuary. So yeah, I changed the speed, and it's very simple. The imagery was provided by CRISA, which is the Center for Remote Sensing and Spatial Analysis at Rutgers, where I was studying, and I produced it while I was at an environmental health clinic, which is a laboratory in NYU. So that's the animation, and how I came to create that was fairly simple. I was interested in the subject. Actually, a law clinic that was representing various constituents that wanted to close down Oyster Creek nuclear facility. That law clinic approached the lab that I was with, and they were interested in doing visualizations, various installations to kind of raise awareness of the issues relating to the nuclear plant. There's many more issues, but we kind of focused on this because it seemed very apparent and kind of easily implementable. And so actually I started by doing a little bit of research locally at Rutgers, and there was a class called Advanced Remote Sensing. This is a while ago. I guess this is still this right here. And you can see that the information is quite dated, but I can share this information for those that want it. It's a pretty good presentation. Some of it is relevant still, some of it maybe not so much. So I started by kind of taking this information and analyzing it, and I know that there was an inquiry about how to calculate surface temperature of water, and I don't know if there's that much of a difference in terms of water versus land. I can imagine there is, but there's a process that you can do, and it's available here kind of in basic form. And this presentation also talks about let's see, conversion, but also correction. So making sure that there's consistency in the reading in terms of measuring temperature. So kind of correction as well. And so in a nutshell, I don't want to go too deep into it. It essentially is taking the radiance value and then converting it into a digital number, and that digital number can then be converted into a temperature. So this is kind of the calculation here. So I started by doing that. I'm trying to understand the temperatures. Actually, I have some initial analysis. Pardon the kind of crappy graphics, but here I was taking the various radiance values and then kind of measuring the things around it. And so the first thing I noticed from the get-go was that there were these kind of marks throughout the mainland, in a sense, warm temperatures, and what I came to realize was that these water bodies have a higher temperature, because it's shallower water, and there's various other reasons. But so I kind of identified these things in comparison, try to kind of not to confuse error, but then also compared them in relation to the plume as well. And yeah, and so that was the initial analysis, and then I also did some other things, and what I ended up settling for, because the calculations were rather confusing, and I didn't want to necessarily get too technical in this animation. I just settled on the pink represents ambient temperatures above ambient level, and I thought that was pretty clear. I mean, what's confusing about it is the fact that throughout the year, the temperatures change. I mean, the ambient temperature changes significantly, throughout the year, and then obviously the plume temperature kind of changes in relation, because obviously the water mixes, and so yeah, I just figured that from a visualization standpoint, it just made more sense to just show the temperature and the plume as it relates to ambient temperature. Yeah, there was kind of a thought process behind that. If anybody else is interested, though, in measuring temperature, I did also kind of pull up some quick resources just through some light online research beforehand, and I think that ArcGIS offers a tool in their toolbox in terms of measuring the temperature, and then also QGIS also offers an extension, so there's an open source option as well. And as the previous presenter, I guess Ned mentioned, these Landsat imagery, or these images are pretty readily available for free now. I think that they were a little bit more challenging to find when I was in school. So yeah, I guess that's pretty nice now that if you wanted to create a visualization like this and have more imagery available, and you probably do something much nicer in a sense. This isn't really related per se to the actual imagery reading, but I also prepared kind of some environmental ecological analysis from that, and so I was mapping the ecological system there, and trying to create like an ecological model in a sense, trying to see what different species were affected. One thing that I hypothesized, I never really studied because I'm not really a full-blown scientist per se. I mean, I'm actually an environmental planner by training, but one thing that I was hypothesizing was the fact that actually, so the oyster population in Oyster Creek was diminishing, and no one really understood why. There's a variety of reasons. Some were attributing the anti-fouling agents in paint liners, or for boat liners, and that was one theory. But also, I was trying to understand how it related to the plant and the thermal pollution, and there was different. If I'm trying to remember this right, there's different species. I guess I think it was certain mussels, or I think something that was actually causing the boats to get eaten. That species was not present before, and because of the pollution and the temperature of the bay, I think that species was more readily available, and I think that was essentially triggering people to then put this anti-fouling agent that they didn't use before. But it could be a variety of reasons, and I didn't really study in full detail. But also, kind of on a funnier note, I thought I'd mention this. We kind of came up with this idea of having a nuclear beach party, where people could actually swim in the water. I mean, the water wasn't necessarily radioactive. I mean, maybe to a certain extent, but definitely swimmable. So you could have a party in the middle of winter, and so that was kind of our fun twist at the end. But the research was then used by this law clinic to do litigation against the plant, and the plant will be closing. It's the oldest nuclear plant in the country. It's a major liability. I mean, if something was to go wrong, the whole entire eastern seaboard would be devastated. And so, you know, it's kind of good news. I don't know if the video had anything to do with it, but that's my presentation in a nutshell. So, yeah.
Thank you.
Yeah.
Does anybody have any questions for Zenon?
Yeah, we're having some conversation here.
I have a question. What does the, I didn't get any sense of scale from the map. Like, what's a pink versus a double pink? You know, like, how many degrees is that? Is it a little, a lot?
Yeah. No. You're looking at the scale of the space. Yeah. I mean, I should have probably put a scale bar there. That would have been a good thing to do. But yeah, I mean, this is the bay. This is Long Beach Island. I mean, for those that are familiar with the area, it makes a little bit more sense.
Yeah, I see what you're pointing at.
Hold on, do screen share again, Zenon.
Oh yeah, I'm sorry. I'm kind of going to the, let's see, screen. Yeah. So I mean, I was just kind of showing the bay. So you know, for those that are are familiar with the area, they sort of know that that's the size of the bay. That's Long Beach Island. This is mainland New Jersey. They kind of it's I think I don't know if it's an island or if it's a peninsula, but you know it's this is where Oyster Creek is, and so yeah, it's a little confusing because yeah, there's no scale bar, there's no sense of relation, and yeah, I mean you can't really tell, you know, you can't really compare the size of the plume to anything else.
Sure. Yeah. Yeah.
Say that a little bit louder.
The temperature scale?
Oh, temperature scale. So
one pink versus two pinks.
Right. Yeah. I mean, that's another thing. So you know, because this isn't super scientific, I didn't really you know include a temperature scale. I mean, as I mentioned here, I did a little bit of research in terms of getting the units. I think I you know switched it to one of the I don't know if that's the digital number, or I think that this was the digital number that was taken from these different levels. So I digitized it. I made it into into digital data, vector data. But
so, Zenon, are those really small numbers? Maybe could you read them out for us, or tell? And also be clear, are those degrees, or is that some?
No. So I think that was the digital number. Again, you know, this was pulled a long time ago. You know, I was kind of playing around with some of this research. So I mean, it could be the digital number. You know, I mean, this was measured, you know, at a certain time of the year. So I mean, it's measuring 118, 133, and then it's then converted to get the temperature. So you can get the plume temperature, you know, in Celsius. Yeah.
Can you read out those? The numbers are really small on the screen. Could you just read out
which
temperature
numbers?
is? Yeah.
These numbers?
Yeah, the plume numbers and the bay numbers that you were just showing us on the slide.
So yeah, I mean, I just got this image that I created early on. This was kind of to understand the temperature at the time, or how to get the temperature. You know, this is 84 to 87, then 87 to 90, 90 to 92. So I'm not entirely sure what time of the year this was measured, but I'm assuming that this was the digital number. You know, again, this is very long ago that I did it.
But in the tutorial though, the tutorial showed, yeah, this one, because this was the exercise, right? So the ambient bay was 12.7 degrees Celsius, and then the plume temperature is up almost 5 degrees higher at 17.2 Celsius, 4.5 degrees higher.
Yeah, well, so that's an example of the difference. I mean, this was you know, done by somebody else, taken by somebody else. So, and it was a different time of the year. So I mean, this could have been during the summer, as opposed to when I did it. You know, maybe when I measured this, maybe it would have been during the winter. So, Yeah.
Great, thank you.
Any other?
Yeah, does anybody have any other questions and comments? With a conversation group here for thermal imagery. Liz, I think you're muted.
Yes, sure.
Oh, sorry. It looked like you were asking a question, and then.
We're talking. What can I say? We're talking.
What value were you comparing? 12 or 17. 12 degrees Celsius. That's
So New York is doing a bunch of temperature conversions in our head, and I guess we're really
53.4 to
yeah. What happened?
okay.
Okay. I don't know. Yeah, we're over here converting temperatures because we're trying to understand the magnitude of the problem with thermal plumes around nuclear power plants. And you know, we were going to have some presentations from Kaya and Sarah, but they're both unavailable tonight. But you know, there's a public lab tool that's being used almost 100% dedicated to studying thermal plumes outside of nuclear power plants. So I guess we're just trying to grapple with how much of an issue is this? Is this some way, you know, a regulatory angle to approach other power plants? You know, how big is this problem, basically?
You want me to chime in?
Anyone can chime in. You don't have to be on the spot.
Yeah, well, I mean, it is and it isn't. You know, oftentimes there could be good aspects of thermal pollution. You have, you know, sometimes increased populations that you know, can thrive, you know, during the winter. You know, it's not always necessarily a horrible thing, but it's messing with the ecosystem, that's for sure. And so it's definitely not keeping things in its natural form, and so that has effects on the ecosystem. Then again, one could argue that nothing's in their natural form anymore and whatnot. But you know, that if you really are interested in you know, keeping a natural ecosystem, you know, an ecosystem that's balanced, and you know, in my case, you know, in Oyster Creek, there was definitely a noticeable significance to the oyster population diminishing and the thermal pollution. But what was the correlation? They haven't figured it out. I mean, I don't know. I haven't followed the project since, but you know, that my theory is that there is something. I can probably find some literature that, you know, also talks about you know, the effects of thermal pollution. There definitely are many. So, but that was through my research. That's what I found. I found that, you know, it is and it isn't that major.
I guess comparing it to natural environments in California, right? Like New Jersey, it's never been natural. What is nuclear power plant compared to conventional power? Like there's oil, gas, natural gas, coal, like in terms of heat plume or things like that, you know? But that, it seems like that would be a better correlation. You don't release wastewater or anything? It should be. Not all.
Liz, can you repeat some of the conversation here? We're having a hard time hearing.
Sure. Do any of you want to move up to the mic? I could share.
Hello. So my question was that rather than compare a nuclear power plant to the natural environment that never was in New Jersey, what is the correlation between a nuclear power plant and a conventional power plant? Like, like anything else that generates steam, like I know they're doing like lots of trash burning ones there, or coal, natural gas, et cetera, and then someone else whose name I can't recall chimed in and says that there is no wastewater from conventional power plants, which strikes me as ridiculous. But maybe there's no coolant, no cooling water, so there aren't any heat plumes from. Right, but you do have. I imagine you have waste heat. Steam, yeah. Powerful enough to generate electricity or things like that, but it's all over New York City.
You guys have to come up to the mic, otherwise you just look like a bunch of mumbly people.
The discussion here, so the first question is, what is nuclear versus non-nuclear, still in the context of power plants? Then we had a voice kicking in saying that, well, conventional power plants don't release any plumes at all because they let it up into the sky, and then someone else says, well, actually, no, they still do need to. So I guess what we need to establish is, I would like to compare the two, nuclear power plant heat plume versus conventional power plant heat plume.
So I can chime in on that if you're interested.
But I don't think so. Sorry?
I can chime in on that if you're interested. So
yes, please.
First of all, in order to have a discharge to the water, you pretty much have to be near a water source. So you'll see power plants in Pennsylvania that are very large coal power plants, but they're just so far inland, they just utilize cooling towers completely. So there's no impact on water bodies. So not surprisingly, you see them mostly on the coast where you can get this this differential of temperature. And then the reason they do the discharge or the non-contact cooling water and the cooling is all part of the steam cycle. So provided the power plant uses the steam cycle, they're heating up water into steam and driving a turbine and then condensing it back down, they're going to use some sort of cooling. So the largest power plants are generally the nuclear power plants, and that's why there's a lot of time focus on them as far as heat pollution. Just the way they're built, they'll build 2 or 3 reactors, and the megawatts can be like in a couple thousand megawatts. The second largest would be the coal power plants. So another example would be like Brayton Point in Massachusetts, which actually, under consent decree by some lawsuits, was required to install 2 cooling towers, where before they just did the heat discharge into the bay, which I think that's Fall River or New Bedford. I always confuse the two. It's in Somerset, Massachusetts. And then another example would be Kendall Power in Cambridge, Massachusetts. Again, it's on the Charles River. So they, I think they're pretty much like oil and natural gas, but they run the steam cycle as well. They have like mini cooling towers on the roof, and then they have what they call chilled cooling power. It's actually just like refrigeration cooling, but then they would also discharge into the Charles River, and they've cut back on that dramatically. They actually hooked up to the steam grid in Boston, and so they'll try and discharge their heat pollution to the steam grid and sort of make use of it. So I mean, it is correlated to the size of the power plant. You can gauge it by megawatts.
So what is the size of Kendall?
Kendall? Yeah. I honestly can't name off the top of my head. Maybe like 350 megawatts. That's a stab in the dark. I have to look it up.
Can I ask, are you looking for data sets to look at this globally, to look at nuclear power plants globally? I'm going to put a link in the chat here to for another time. But the bureaucracy of NASA is difficult, but there are 13 data centers, and this POPAAC is a physical oceanography data center, and there's 3 or 4 different satellites that have data sets on sea surface temperature. And I think an interesting project might be, also just visualization, is to take a look at globally sea surface temperature over time at the in the coastal environment off the coast of these nuclear power plants and see what you can see. That would be pretty interesting. I mean, if people have done that before, I doubt they've put together a good visualization of it.
Well, as long as a power plant is using steam cycle, which, to my understanding, most power plants are, is the correlation directly between how many megawatts a power plant produces and how much heat, waste heat, it dumps into the ocean or into the body of water, or are nukes special in some kind of way?
Well, no. So most plants in the United States will have some sort of I don't know what you call it, like a mitigation where, like a cooling tower. So a cooling tower, the whole point of a cooling tower is it releases the heat into the air and not into the water. So you'll see that quite often. Like the nuclear power plants, they have those iconic cooling towers to big, like hourglass-shaped type devices.
I have a question. Is thermal pollution considered in part of the NPDES permits, the National Pollution Discharge Elimination?
Yeah, I really don't know. So this is kind of outside of my expertise.
Does anybody know about that? Like, where are the regulations in terms of thermal pollution?
They're very lax, at least in New Jersey. I know that they really weren't using that as a way to regulate the nuclear facility. I know that the DEP here really didn't do anything about that. But it could vary in different states.
I don't think the EPA regulates temperature. It's pollutants. So I don't think that's part of that permit.
The sense we got from when we were at the barn raising up with our partners on the South Shore of Massachusetts, it seemed like these were sort of like the regulation of how much thermal wastewater is released by power plants was sort of like a backroom deal, or like kind of a soft negotiation point. Both in that, like, it seemed like there weren't hard standards that were being applied to what they were allowed to do by permit, and then also in that it was more of a leverage point that some of the interest in these thermal plumes being released by nuclear power plants are being studied as a way in to put pressure on other aspects of their operations that the community is pleased with. Did anyone else get that sense from talking to our community partners in the Northeast about it? Maybe some Boston people?
Yeah, the position of Cape Cod Baywatch is that, and I pasted in a link to the Wikipedia article on the Pilgrim generating station, which has a whole section on the environmental impacts. But the position of Cape Cod Baywatch is that the regulations that are actually allowed them to be re-permitted, if enforced, would require them to have a closed-loop cooling system. But they're simply not being enforced. So I guess maybe that's what Liz is referring to in terms of back room and so forth. In some cases, though, I think depending on the agency, correct me if I'm wrong, but I think the EPA has some authority to regulate, for example, spray adhesives in the workplace, or or no, I'm sorry, that was OSHA. But there are cases where like the agencies are limited by resources in terms of what they actually do regulate, like because it requires them to send someone out and to open a case and so forth. So it may be related to that, but I think that it's too bad. Are Karen Vale or Pine Du Bois here? Because I noticed Karen has edited the wiki page on doing thermal analysis of Cape Cod Bay like within the past 7 hours. So I think did I paste that in the chat as well? Here.
Sure.
Wow, that's super helpful. Thanks, Jeff.
So I'm just pasting in a bunch of links to the chat room here, but so check them out.
And I know that one of the things that they were specifically talking about at Pilgrim was not just the thermal pollution, which is a big issue for them as well, but that they use it to cool. They're sucking in all this water to cool off their equipment, and it's that everything that they're pulling in is includes small fish and larvae, and so it's both ends of that. And in a closed loop system, I think it would still release heat. It would reduce that sort of intake that they're seeing happen right now.
Yeah, and trapped organisms. Another thing that's worth mentioning is when they shut off the plant, oftentimes during the winter there's a shock that a lot of organisms receive, and oftentimes there's mass killings of fish and whatnot. And so actually the plant gets fined, or I know that Oyster Creek has gotten fined in the past for shutting off the plant and killing a lot of fish and other organisms. So that's a problem as well. And the dissolved oxygen, there's much higher dissolved oxygen. You can read it. I just looked it up on Wikipedia, so it's on the side.
I'm just going to jump in for a second. It has been an hour. It has been the open hour. So I'm happy to stay on and continue, and it's a great conversation, and I'm really engaged. But if people are going to drop off, I just wanted to say thank you for coming, and I really enjoyed the conversation and the presentations. And so I'll leave it open, but I just wanted to say thank you before anybody left. So were there any other thoughts or questions on for Ned or Leela or on this topic of thermal pollution? I feel like I just stifled the conversation there.
No, I think we're just excited about we're really missing our people of the thermal fishing bob. Both Karen Bale of Cape Cod Baywatch, like Jeff was mentioning, and also Kaya Simmons, the technologist and educator working on it, or even Sarah or Imond. So I guess, and because that's actually Public Lab's main tool for approaching thermal imagery. So I guess I'm just excited for a future event where they get to, explain the technology they're applying to this issue.
Right.
So, I kind of walked in the middle of this, but I'm wondering if people are looking much at other pollution besides thermal pollution.
Yes.
In, like, actual radiation, or I don't know what.
Yeah, I think that's a big concern, and especially with just our recent exposure with Public Lab to the Pilgrim plant. It is a form of pollution that comes from this industry, and although there are a variety of other things, it's sort of like another leverage point to actually deal with some of those big issues like you're talking about. Just something else, and it's not to sideline any of those other really pressing concerns, but just another aspect that maybe isn't weighed in as often.
Yeah, I mean, we had a whole previous call dedicated to open water, which is all things water sensing. I don't think anyone is working on radiation, but one of the reasons we pulled out thermal imagery in particular was that it's relatively low tech, and it can be applied to multiple issues. For instance, as a way to enforce regulation against nuclear power plants by getting them on the extent of their thermal plume. Also, as a way to identify combined sewer overflows in the city, which come out warmer, but are otherwise invisible. So without requiring a bacterial test or anything like that, just with simple thermal imagery, you can actually get at, you know, a lot of really big issues that are invisible to people's regular eyeballs.
And those of us who have irregular eyeballs.
Was there a question earlier about NIPD's
Yeah.
permits and the EPA and temperature?
About the, say that again?
Well, did you ask a question earlier about the NIPD's permits and the, yeah, so temperature is one of the Clean Water Act. So if you have access, I mean, you probably already are on the, you guys already know how to log into the EPA system and everything. So, I mean, I don't know what that means, how often they test, but there should be some information for every NIPD's permit.
Cool. Thank you.
Yeah, but I think every state may be a little bit different. You know, I mean, all they have to do is be the bare minimum. And I don't think it's actually a standard. I think that they just have to report. I don't know if there's a federal standard. But I think as part of their NIPD's permit, they have to report what the temperature is. So it may be that the states have their own standard. It might not be that the Clean Water Act actually specifies the temperature.
Great. Thank you.
Also, maybe as a sort of a closing thought, I know Don Blair and a few others, you know, at the Northeast barn raising, I'm putting a kind of an obscure note into the chat here, but take a look at it. And there's been a lot of attempts to make really, really cheap thermal fishing bobs, where, like, you know, it's a device that lights up in a color that corresponds to the temperature. And he posted a design that, based on a sketch we came up with in the barn raising, that could be like under $5 for the entire device. And it's pretty neat. It doesn't use any microcontrollers at all. It just uses a sort of a timer. So anyway, if any of you are into electronics, I think Don has ordered a few of these, and they made them at one of the recent local open water events in the Boston area. But yeah, it's kind of neat, and I think it means that you could, like, you know, before too long, we should be able to, you know, make or buy dozens of these at a relatively low cost, which is pretty cool.
Great. All right. Well, thank you. Thanks for everything.
Thanks, guys.
Thank you.
Bye.
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 All right, thanks, everybody.